Hello everyone. I'll be talking about a work, dimension independent and computationally efficient shadow tomography. So first, let's start by defining the problem of shadow tomography. Simply put, the setting is as follows. There's an unknown quantum state rho and you can ask for copies of it. You're also given a list of POV elements P1 through Pn. You're supposed to output the estimates for the expected values of these with respect to the unknown quantum state rho. This problem can also be formulated in terms of observable expectations, but here we only work in terms of POVMs. If you are given observables, you can simply scale and shift them to make them into POV elements. Now, in the classical case, that is when all the POVM elements commute, we know that we can perform all POVMs simultaneously and obtain empirical averages, leading to the number of copies required, that is the sample complexity, being log m over epsilon square. However, in general, if we proceed naively, we will need log m over epsilon square copies for each of the POM elements. And since the POM elements might not commute, we will need fresh copies of rho for each of the estimations, blowing up the sample complexity to m log m over epsilon square. So now, one might ask, is it even possible to improve upon this? And for that, we have to figure out some ways of reusing the same copies for different measurements. Now, there are already some existing algorithms, and I'll give a brief overview of some of them. First, we have the classical shadows algorithm by Huang, Quang, and Preskin. The algorithm is as follows. For each of the received copies, randomly choose an orthogonal basis with respect to some fixed distribution, and then measure in that. Next, once you have all the outcomes, take their pre-images with respect to the overall measurement channel induced by the measurement procedure. Finally, for each of the POV element Pi, compute the expectations with respect to these inverses, and on these values, use the medians of mean estimator to get the final estimates. This algorithm works when the number of copies is capital M square log m over epsilon square. Here, capital M is a quantity called the shadow norm, which depends on both the chosen distribution as well as the list of POV elements. In general, for certain distributions, this can grow in the worst case to square root d, which can make the overall sample complexity d log m over epsilon square. This is optimal in m and epsilon, but very suboptimal in d. Next, we have the ones utilizing noisy measurements. The main kind of behavior these algorithms go for is given by the gentle measurement lemma, which states that if a state rho has an almost certain outcome with a POVM, then conditioned on that outcome, the perturbation with respect to trace distance is also small. What this means is that it allows you to perform certain quantum measurements without much perturbation to the state, allowing for reuse. In case of shadow tomography, the most common kind of check involves a testing version, where you check if your original estimate was good enough. These algorithms use noisy measurements to improve upon the performance guarantees of just the gentle measurement lemma, and the best sample complexity of such an algorithm is currently attained by the one given by Berdowski orthogonal, which is log square m log d over epsilon to the fourth. Now, for both of these algorithms, we saw that even though they can perform better than the naive approach in certain settings, the sample complexities feature an additional dimensional term. So, a natural question that arises is this dimension dependence necessary? That is it true that definitely doing better than the naive approach in a regime requires having a dimension dependent term? Answering this question was the main aim of this work, and we find that the answer is negative. We do this by exhibiting a shadow tomography algorithm which has sample complexity square root n log m over epsilon square. This is strictly better than the naive algorithm, and the complexity is clearly independent of dimension. Furthermore, Our algorithm does not require any d-dimensional linear algebra, unlike the other ones discussed. Next, our algorithm can also be implemented as a read-once quantum circuit, where the copies come one at a time and the working space is limited to just m log n ancillary qubits, n being the total number of copies. Finally, the gate complexity is also bounded with only n queries to the POVM circuit and n log m over epsilon square copies per estimation. The key ideas used for the algorithm and the corresponding analysis is as follows. We revisit the idea of using noisy measurements to limit collapse, but instead of seeing perturbation with respect to trace distance, we try to see how the expectation values themselves change. We call this gentleness in shadows. Next, our algorithm involves very independent estimation procedures for all the POVMs. So, we argue for correctness of each estimate individually and then bound the total probability of failure via the union bound. As a result of the previous statement, we can make virtual changes to the algorithm that do not impact the correctness of the specific estimate that we are working with. We will now describe the algorithm in parallel with an overview of the analysis. For m PM elements, we are going to perform the estimations in m rounds, one round per estimate. At the start, we will have n copies of rho with n to be determined later. Now, in each round, we will ask for a fresh set of k ancilla qubits, discarding the previous ancillas. For this algorithm, we keep using all of the copies of rho. Also, for simplicity, in the STOC, we will restrict to the case of projectors instead of POVM elements. Now, for any projector P, define P control rotations as the quantum gate acting on a control register and a target qubit as follows. It acts as identity on the target qubit when the control register is in the zero eigenspace of P, and acts as some Rx theta on the target qubit when the control register is in the +1 eigenspace. We will now describe the algorithm first in the case when we are given only a single expectation to estimate. From each of the n copies of rho to each of the k ancilla qubits, we apply the P1 controlled rotation gate, leading to a total of n times k many of these gates being applied. The rotation parameter for all of these gates is theta, which is also to be determined later. For the case of n equals 2 and k equals 4, this is how the circuit looks. Here, think of the usual control as just the P1 control. After applying these gates, the k ancilla qubits are all measured in the computational basis. This describes all the quantum parts of the algorithm. Now, before we describe how we use the measurement outcomes, let's first analyze the situation a bit more. Notice that the correctness of the estimates depends only on the statistics of the measurements and the ancillas. Since we only apply the P1 controlled rotations, we can assume that we had measured out the copies of rho with P. Once we do that, we can replace these P1 control gates with just Rx gates with rotation dependent on the measurement outcomes of rho. Here, theta I is the outcome dependent rotation parameter, which is 0 if the measurement on rho failed and theta if the measurement succeeded. Note that with this, we get that the expected value of theta I is directly proportional to the value to be estimated. Now, if you look at the circuit carefully, you'll see that all ancillary qubits contain the same pure state, which is Rx sum theta I applied to get 0. Here, by definition of theta I, we know that the sum is directly proportional to the empirical mean for P measurement on rho. Since the empirical mean is a good estimator, it suffices to estimate some theta I as well. Now note that on computational Bayesian measurement for each of the ancillary qubits, we get a Bernoulli random variable with probability sine square half sum theta I. Therefore, with measurement of all of the qubits, we get the binomial distribution with parameters k and half sum theta I. So, for k large enough, we can easily estimate sine square half sum theta I. Finally, it turns out that the inverse of the function sine square x, which is arc sine square root x, is Lipschitz in the regime of our interest, which means that we also get a good estimate for sum theta I, which finally means that we get a good estimate of the empirical mean. This leads to the following result, that for m equals 1, our algorithm works for n equals log 1 over delta over epsilon square, and k also being equal to the same value. We now describe how the algorithm works when we have multiple expectations to estimate. Effectively, what we do is that we repeat the process m times, reusing all copies of rho, pretending that they are unperturbed. It isn't immediately clear why this should work, so let's see an overview of the analysis as well. Note that we analyze the correctness of the algorithm one estimate at a time. For now, fix any pi whose expectation estimate we verify to be correct. This estimate will come from the measurements in the ith round, so we can ignore all rounds after the ith round. Furthermore, we now have to see how exactly our copies of rho got perturbed in each round j before I. Also, assume that at the beginning of each round j, the state we have is n copies of some quantum state rho j. We'll see later that this assumption is not entirely baseless. We redraw the circuit from before for the ith round, except we're starting with rho j's this time. Right now, we don't really care about the measurement outcomes in this round, as they don't affect the estimate in round I. Therefore, we can pretend that we simply trace out the ancilla qubits in round j. In fact, we can do something stranger. Instead of tracing them out, we can instead measure them in the ket plus ket minus basis. We specifically chose this basis because these are the eigenvectors of Rx. What this gives us is that this measurement commutes with the pi controlled rotations, and thus we can further pretend that the measurement started at the beginning of the round. Now, if we measure out the ancilla qubits at the beginning, we get the states ket plus and ket minus with probability half each. Note that this measurement in itself doesn't perturb the states rho j, and thus we can further instead pretend that we started out with each ancilla in state either ket plus or ket minus with uniform independent probability. Once we do this, notice now that none of the pi controlled rotations have any effect on the ancilla qubits, as all the states are eigenvectors of these pi controlled rotations. However, whenever such a thing happens, we get a phase kickback onto the control registers. If we compute out the phase kickback, this is how it will look. Note that here, lambda L's are eigenvalues of x corresponding to the eigenvector in the Lth ancilla qubit. That is, lambda L is plus 1 if the qubit was in state ket plus, and minus 1 if it was in state ket minus. What this tells us is that conditioned on the initial states of the k ancilla qubits, the perturbation has a product structure. So, the product structure of the input states is maintained, and we can write out the output states as n copies of some rho j plus 1, which depends on both rho j and the state of the ancilla qubits. Since the input states of the ancilla qubits are chosen at random, what we can say in general is that throughout the running of the algorithm, the state remains a convex combination of n copies of IID quantum states. With this, remember that our goal was to bound the perturbation in expectation values. At the beginning of round I, the state is rho I, so what we really need to do is bound the quantity trace pi times rho minus rho I. We can write this quantity as a telescoping sum of perturbations accumulated in all the rounds before I. Note that we are trying to bound the perturbations with high probability, and the only source of randomness in this argument is the choice of input states of the ancilla qubits. This randomness is equivalent to choosing each lambda L as plus or minus 1 with equal probability. Let us focus on one of the terms in the sum. For that, we first write down the first order approximation of the phase feedback in theta. Here, I am simply using the approximation for e to the x as 1 plus x. With this approximation, we get rho j plus 1 as a function of rho j as follows. Here too, we only work with the first order approximation, so we drop the theta square term in the approximation as well. Feel free to verify this computation. Plugging this into the perturbation expression by linearity of trace, we first get this new expression. Now, we can further rewrite the expression inside the trace in terms of commutator of pi and pj as follows. In this expression, note that the distribution of some lambda L is basically a binomial distribution shifted to zero mean, as each lambda L is plus minus 1 with uniform randomness. When we sum up these perturbations, we are effectively summing up these binomial-like distributions, so the sum is also similarly concentrated around 0. To formalize all of these arguments, we need to bound lower order terms and use some martingale concentration bounds, and that gives us our result. Note that the number of ancilla qubits k is much smaller than n. This is because we do not need to increase k to increase accuracy of estimates at each round. And in fact, increasing k is detrimental, as more ancilla qubits implies more perturbation. Having discussed the result with respect to sample complexity, let's now talk about the implementation details. First, note that each p control rotation can be implemented with the circuit given for measuring p. I'll refer to each use of the circuit or the inverse as one query. Now, if you were to naively implement the algorithm, since it uses n times k p control rotations at each round, the total queries to the measurement circuits is m times n times k. Using only k ancilla qubits suffices, as they get measured at the end of each round and thus can be reused. Now, instead of implementing a controlled p rotation at each time, we can simply store the answer for p in an ancilla qubit and then apply control rotations from that. This reduces the total queries down to n times m. Alternatively, if we don't do that, we can reuse ancilla qubits for measurement in the same round, leading to only O1 ancillas. Now right now, the algorithm was presented in round by round fashion for each of the estimations. If you notice carefully, any two pi control rotations with control on different copies of rho compute. This means that we can instead change the rounds to be per copy, and at the end of each round, we throw away the copy and ask for a new one. The drawback of that is we cannot reuse the ancilla qubits for different estimations, and the total number of ancilla qubits grows as m times k. This number is still dimension independent, which means it's not possible that we are effectively copying a state in memory. Also note that with the variation of the presented algorithm, we can bring down the working space for this to instead n log n. So, to summarize, we demonstrated a new result showing that shadow tomography can be achieved with only square root m log m many examples, which is strictly better than the naive one. Currently, this is the only known algorithm with dimension independent sampling complexity better than the naive one. This algorithm also only requires very standard arithmetic operations, unlike other shadow tomography algorithms whose computation grows polynomially with dimension, and thus exponentially with qubits. Our algorithm can also be implemented as a read-once quantum circuit with memory independent of the dimension as well. The main idea behind the algorithm and the analysis was the use of noisy measurements and the notion of gentleness in shadows. This brings us to the end of our talk. Thank you for listening.